Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know about probability for our upcoming test. So let's start with a question like this. In a class of 30 students, 12 play AFL, 9 play basketball, and 13 play neither. What I'm going to first do is put this information in a two-way table or a Venn diagram. It really doesn't matter which of those that you use because they do the same thing. Two-way tables and Venn diagrams are what we use when we have questions involving two sets. Here we have set of people playing AFL, one set, the other set is set of people playing basketball. Two-way tables and Venn diagrams just allow us to visually display the information to help with probability calculations. So let's start by creating a Venn diagram. So Venn diagrams have two circles within a rectangle like this. So one set will be people who play AFL, the other basketball. So you might be sitting there thinking, hang on, this doesn't make any sense. How can we have 12, 9, and 13 in a class of 30? 12 plus 9 plus 13 equals way more than 30, it's 34. So what that means is we have overcounted by 4 because we've got 34 in total and there are only 30 students. However many you've overcounted is how many are in both. The only way this is possible is if you counted 4 students in the AFL group and then again in the basketball group. So however many you've overcounted goes in the middle. So for the AFL circle, I need 12 in this circle. So I've already got 4 in the circle, I need 8 more. Similarly, the basketball circle needs to have 9 people. It already has 4, so it must have 5 more. Now those 13 that play neither go outside the two circles. Note 13 plus 5 plus 4 plus 8 does equal 30. So I could just as easily have put this in a two-way table. Again, two-way tables and Venn diagrams do the same thing. If I'm drawing up a two-way table, the two ways you can be in the AFL set or not. Secondly, you can be in the basketball group or not. Two-way tables have an extra row and column for the total. So the number that play AFL and basketball, those 4 go here. And then the number that play basketball but not AFL go there. Number that play AFL but not basketball, and the number that play neither go there. So basically you can see that these 4 numbers here are the same as the 4 numbers in the Venn diagram. That's why it really doesn't matter which one you use. So just adding up the totals, 4 plus 5 is 9. So I'll put a 9 here. 8 plus 13 is 21. So adding up all these, we get 30 as well. It doesn't matter which you use, a Venn diagram or a two-way table. So we're now going to use this to do some probability calculations. So we're going to start by calculating this. So every time you see this symbol here, I want you to read it as AND. This N means intersection, read it as AND. This is saying if I select a student at random, what's the probability they play AFL and basketball? Well, we can see from both of these that there are 4 such people. But whenever you're asked for a probability, you must give an answer between 0 and 1. You can't have a probability of 4. The probability is 4 out of the 30 in total. So if you're giving a fraction as your answer for probability, make sure it's simplified. You can give probability as a fraction, decimal, percentage, I don't mind, but if it's a fraction, got to be simplified. So let's now calculate this probability of A union B. Whenever you see the U, I want you to read it as OR. This is saying what is the probability someone plays AFL or basketball or both. Or in maths, this symbol union includes those that play both. So in the Venn diagram, it's these 3 numbers. In the two-way table, it's these 3. 8 plus 4 plus 5 is 17. So there are 17 students that play AFL or basketball or both out of 30 in total. You can also think of A or B as the students who play at least one of those two sports. So don't that this symbol here, the dash, means not. This says probability not A. So what's the probability if I select a student at random, they don't play AFL? Well, there are 5 plus 13. There are 18 students who don't play AFL out of 30. And once again, if writing an answer as a fraction, make sure it's simplified. So we also learned conditional probability. So when you see this symbol between A and B, this symbol here, read it as given. This is the probability of A given B. It is conditional. It's saying B is a condition. What does that mean? It means that the person has to be in B. I am saying if I pick someone random who I know is in B, who I know play basketball, what's the probability they also play AFL? So I'm picking one of these 9 basketballers at random, and I'm saying, what's the probability they play AFL? Well, there are 9 basketballers to choose from. 4 of them play AFL, so it's just 4 over 9. I'm saying, what is the probability? If I know I'm in this circle, what's the probability I'm also in that circle? That's how we do conditional probability questions. All right, let's now take a quick look at independent events. So if 2 events are independent, this means they don't affect each other. One event happening doesn't affect the chances of another. And if A and B are 2 independent events, the probability they both occur is the product of their probabilities. It also means the probability of A given B equals probability A. It means that B happening doesn't change the probability of A. That's a bit hard to understand, so hopefully you will understand better after these examples. So if I toss a coin 6 times, calculate the probability that all 6 are heads. The idea is, when you toss coins, the outcomes are independent. It doesn't matter what happened the last time you tossed a coin. That doesn't affect what happens this time you toss a coin. So, because these events are independent, we can find their probability really easily. The probability that you get heads 6 times in a row is just the product of their probabilities. It's just a half times 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 a half. Of course, there's a much easier way to put that in your calculator. 1 over 2 to the power of 6. 1 over 64. Because the outcome on each toss of the coin is independent, to find the probability I get this and this and this and this and this and this, to find the probability all of these happen, I just take the probability of each, which is a half, and multiply them together. If I roll a die twice, calculate the probability I roll a 6 on only one of the rolls. So again, each time you roll a die, the outcomes are independent. It doesn't matter what you got last time you rolled the die. That doesn't affect what will happen this time. So what we're looking for here is either I got a 6 on the first roll and I didn't get a 6 on the second, or the opposite. I could get something other than a 6 on the first roll and then get a 6. So what's the probability of this happening? Well, because these 2 events, getting a 6 and not getting a 6, are independent, I just multiply their probabilities. So the probability you get a 6 is 1 over 6. Probability you don't get a 6 is 5 over 6. See, what you'll actually see here is that this will be the same. It'll be 5 over 6 times 1 over 6. The probability that this and this happens is just 5 over 6 times 1 over 6. So the probability that either this or this happens, now I'm looking at or, not and, it's just these 2 added up. 5/36 of the time this will happen, 5/36 of the time this will happen. So the probability that we require is 5 over 36 plus 5 over 36. Probability this or this happens is 5 over 36 plus 5 over 36, which gives that. All right, let's look at this question. I pick a card from her deck of 52. Are the events I pick hearts and I pick an ace independent? So what we're going to do is use this definition of independent. What I'm going to do is calculate the probability that I pick hearts given that I pick an ace. So the formula, if you need, for conditional probability, it's the probability they both happen goes on top, And on the bottom is the probability that the second thing happens. So the probability, if you pick a card, that it's hearts and an ace. How many cards in the deck are hearts and an ace? Well, there's only one of those cards out of 52, the ace of hearts. Similarly, the probability that you get an ace, well, there are actually 4 aces in the deck out of 52. So you can put this straight in your calculator, and you should get 1/4. So if you pick an ace, the probability that it's hearts is 1/4. But hang on a minute, the probability of picking just a hearts is also 1/4, because there are 4 suits: hearts, diamonds, clubs, and spades. One of them is hearts. See, the idea is that picking an ace, knowing that the card was an ace, didn't change the probability that it was hearts. If you pick a card that's an ace, you still have a 1/4 chance of picking hearts. That's why these two events are independent, because the card being an ace doesn't affect the probability that it's hearts. All right, let's now look at the OR rule for probability. So the OR rule for probability says probability of A or B. You add the probabilities and minus the probability that both happen. So let's try this question. We're going to calculate probability A or B, where probability of A is 0.1 and probability of B is 0.5. So part 1 says that they are mutually exclusive. So 2 events are mutually exclusive if they can't both happen at the same time. So an example of this would be you getting an A in maths this semester and you getting a B in maths this semester. They are mutually exclusive because they can't both happen. You can't get an A and a B this semester in maths. So if 2 events are mutually exclusive, the probability they both happen is 0. So if A and B are mutually exclusive, the probability that A or B happens is just 0.1 plus 0.5. In this case, I don't need to subtract this part here because it's 0. So it'll just be 0.6. So what about if A and B are independent? Well, we learned on the previous slide, if A and B are independent, to find the probability they both happen, we just multiply the probabilities together. So 0.1 times 0.5 is 0.05. That's the probability both happen. So the probability that A or B happens, what we do is we just add together their 2 probabilities, but this time we need to subtract the probability that both happen. So if you want to use your calculator, that's fine, get 0.55. So if A and B are mutually exclusive, you don't need to subtract the probability that both happen because it's 0. But if they are not mutually exclusive, then you do need to subtract that. All right, let's now take a look at tree diagrams. So we previously looked at Venn diagrams and two-way tables. We use those when you have events involving multiple sets. You use tree diagrams when you have events involving multiple stages. So in this question, bag contains 5 Mars bars, 4 crunchies, 3 chocolates are picked with replacement. This is a multi-stage event. It's occurring in 3 stages. I'm picking 1 chocolate, first stage, second chocolate, second stage, and then picking a 3rd chocolate. What tree diagrams do is they help us organize and list all of the possible outcomes. So we'll draw them like this. So let's start with the first pick. I can either get a Mars bar or a crunchie. And then of course, from the second pick, whatever I got on the first, I can get Mars bar or crunchie. And then I have a 3rd stage here because I'm picking 3 chocolates. Again, I can get Mars bar or crunchie. So we stop after this 3rd stage because I'm only picking 3 chocolates. So to list all of the possible outcomes, what we do is we go through all the branches. So there's MMM, that's one outcome. Then the next one is MMC, and so on. So here I have 8 different outcomes. But there's a problem. The probability of each of these is not 1 over 8. Why is that? Because each of these is not equally likely. At each stage, it's more likely I pick a Mars bar. See, there are 9 chocolates in total, 5 of which are Mars bars. So I need to put a 5 over 9 every time I pick a Mars bar. And then a 4 over 9 every time I pick a Crunchie. So how do I answer this question, the probability that 2 Mars bars and 1 Crunchies are picked? Well, first I'm going to identify the outcomes where 2 Mars bars and 1 Crunchie are picked. To find the probability of each of these, I multiply the numbers on their branches. So for MMC, I go 5 over 9 times 5 over 9 times 4 over 9. So that equals 100 over 729. What about the probability of MCM? Well, I've got 5 over 9 times 4 over 9 times 5 over 9. That's the same answer. It's also going to be 100 over 729. And then similarly, this will be 100 over 729. All of them involve multiplying 2 5 over 9s and a 4 over 9. So the probability this or this or this happens, well, these three are mutually exclusive. You can't get this and this at the same time. So to find the probability that any one of them happens, I simply add together their 3 probabilities. So I go 100 over 729 plus itself 3 times. So putting that on our calculator, we get 100 over 243. And that's about 0.41. So that's how we draw tree diagrams and use them to calculate probabilities. Now we need to know the difference between with and without replacement. So in this case, it was with replacement. That means if you pick a Mars bar the first go, it's replaced in the bag by an identical Mars bar. What about if instead it was without replacement? Well, you'd still follow the same process, but these numbers here on the second and third outcomes would change. If it was without replacement, if you picked a Mars bar, there would be 4 out of 8 Mars bars left, 4 out of 8 Crunchies. There would be here, if you picked a Crunchie, 5 out of 8 Mars bars left, 3 out of 8 Crunchies. All that would change are these numbers on the branches in the second and third stages. But you would still list the outcomes the same. You would still multiply the branches to come up with these probabilities, and then you'd still add these together. But just make sure that you can do questions both with and without replacement. All right, thank you so much for tuning in. Best of luck studying for your test, but you'll ace it, you're a star. This has been the luckiest maths teacher in the world. Have a great day.